Okay, in the previous lesson on thermal energy, we kind of laid the foundation to talk about heat exchange. And we kind of introduced how we quantified um, heat energy. And we called it M mass times C, specific heat capacity, times the change in temperature. And so now we've got a formula for it. We can quantify it. And now what we're going to do in this lesson is we're going to talk about heat exchange. So it's basically when two objects are in contact, in thermal contact, one of them is giving up some heat energy and another one is gaining some heat energy. And so this is really just like the conservation of energy. It's the law of conservation of energy, but applied to heat. And so this is what we do, okay? This is how we quantify it. We know that the heat energy that's gained by one is going to be equal to the heat energy that's lost by the other. Because that's what the conservation of energy tells us. The heat's got nowhere else to go. We're assuming a closed system, right? So we're not going to lose any heat to the environment or anything like that. And so the way that we do this is we take the heat energy that's being gained, and that's equal to the heat energy that's being lost. And in the final lesson, in the final example of yesterday's lesson, anything that's losing heat energy, we've got to put a negative sign there. So we should be getting more and more comfortable with positives and negatives for energy. And basically what we're going to say is that we're going to say, okay, well, here is a negative sign for heat energy. And so the negative sign in the second equation represents the direction heat is flowing, right? So this is a convention. So we always say that when an object is losing energy, we give it the negative, right? And so heat always flows from hot to a cold, right? We place the negative sign here because this thing is losing energy, okay? So what we're going to do is we're going to work with this now, and we're going to work with the concept that we learned yesterday, this heat energy equation. And we're going to try and look at a couple examples. So we have two examples coming up. The first one is basically hot water for tea, right? Basically, we have a half a kilogram of hot water, and it's cooled down to 40 degrees Celsius, which is no good. If you're making tea, that tea needs to be hot, okay? So how much freshly boiled water at 100 degrees Celsius must be added to bring the temperature of that tea up to 65 degrees Celsius? So not too hot, but also not too cold, because this is pretty cold for tea. All right, so this is what we have. Here's our tea in here. Here's our kettle, right? So here's our teapot. Initially, this thing right here is at 40 degrees Celsius, right? So here it is. We got half a kilogram of water in here. It's at 40 degrees Celsius initially, and I'm going to pour some water from here, really super hot water from here, into here, and it's going to bring it up to 65 degrees Celsius. I know what the specific heat capacity of water is. How do I know that? Because I looked it up in the textbook. And in all your homework problems that you're going to try in class with me, of course, you're going to have to look these things up in the textbook, okay? So now this guy over here, this really hot water that's in the kettle, we don't know how much mass this is. That's what we're being asked to find, how much freshly boiled water. But we do know that its initial temperature is 100, and this one's going to cool down. So it's going to cool down to 65 degrees Celsius. And because this is tea water and this is boiling water, really, we can just use the same specific heat capacity. The tea leaves aren't going to change the specific heat capacity enough to worry about shifting CW for both of these. So we're just going to use the same constant. And here we begin. So we start with our statement of conservation of energy, is that the heat energy that's gained by this water is going to equal the heat energy that's lost by this water, okay? So this one, again, is heat gained, and that's why this one's plus. And this one is heat lost, and that's why this one's negative, okay? So just so that we see that, it's very, very clear. All right, same temperature, same formula, MC delta T equals minus MC delta T. And of course, look what you're going to see. The CWs will cancel out, so we didn't need to worry about them. 0.5 is the mass of this, and this is going from T2 to T1, so T2 minus T1. This one over here, T2 is 65 minus T1 is this. Now you'll see it's a good thing that we put that negative sign in here, because this negative and the negative that you get in this bracket will cancel each other out. So we get 12.5 is equal to 35 M, and we'll solve And it turns out that M is equal to 0.357 kilograms. So we know that we need to add about 0.36 kilograms of water, 360 grams of water. Okay, let's look at next question. Hard-boiled egg has a specific heat capacity of 2.4 times 10 to the 3 joules per kilogram degree Celsius. It has a mass of 50 grams. And because when you, of course, hard boil an egg and you take it out of that boiling water, it would be at 100 degrees Celsius. So basically, we need to cool it down if we want to eat it. So we take this egg that's at 100 degrees Celsius and we put it into 1 liter of water at 5 degrees Celsius. Those two things are going to exchange their heat energy and they're going to come to rest at some temperature in between 100 and 5 degrees Celsius, right? So the egg is going to be cooled down, right, by the cold water. But this cold water is going to be warmed up a little bit because we're putting a hot egg in. And we're going to find the final temperature of these two objects after they've been allowed to sit for a few moments. Now, when you think about an egg, you get 50 grams, right? You know how big an egg is. You think about a liter of water, think about a bag of milk, right? Or a quart of milk or whatever it is, like, you know, one of those cartons of milk. Is the final temperature going to be closer to 100? Is it going to be closer to 5? So think about this logically, because we're going to have to analyze our answer afterwards. So let's think about it. You've probably got a guess. Well, here we have the egg. We know its specific heat capacity. We know its mass. We know its initial temperature. We don't know its final temperature. That's what we're trying to find. We've got their water. Specific heat capacity for water. Again, I would have looked this up in the textbook. We've got its mass. We needed to know that 1 liter of water is converted through density. Water is 1 kilogram per liter. So 1 liter of water translates perfectly to 1 kilogram of water. And we know the water's initial temperature is 5 degrees Celsius. T2 is what we're looking to find. So here we again we start with our conservation of energy. The egg is the one that is losing energy, so it's going to be over here. The water is gaining energy. So we bring the water over here, we bring the egg over here, and you can see I've used subscripts to differentiate between the two. And so here we have all of our values substituted in. And we can simplify. And remember that 0.05 times this is a coefficient. This needs to be distributed through here and here, right? This is a coefficient. And it needs to be distributed through here and here. Okay, so this is what we get. We can rearrange, collect like terms, and we can solve. Now, this isn't particularly difficult algebra, but there's a lot of steps, and there's a lot of places to make silly mistakes. So make sure that when we try the questions in class and for homework that you're getting enough practice, because you will definitely be seeing questions like this over and over again on tests, on labs, and on assignments, okay, and in the final exam. So we come to the final temperature as being 7.6 degrees Celsius is our final temperature for the hard-boiled egg. And we have to say, why is this value so much closer to the temperature of the water than the temperature of the egg? And of course, we could say, okay, we already thought about this. This makes so much more sense. There's a heck of a lot more water to accept this tiny bit of thermal energy from the egg. And so because there's a lot more water, it means that the temperature difference isn't going to be quite as large for the water as it is for the egg. There's a lot more water to accept the heat. Okay, that's it for today. Until lesson number 8.